Okay, guys, let's go ahead and start the class. And you can always talk about your vibration homework later. This is vibration homework, right? Yeah. Okay. You're having a hard time with it?
Yeah, it's just like it's a lot. His homework was a little rough. Could have started earlier though. Definitely.
Well, it still wouldn't have mattered if we would have been stuck on 8.
Yeah.
Whichever one he sent that email like midnight last night.
Okay. So we are going to finish the flight mechanics part of the class today, and we will talk a little bit about the exam. If we had enough time, we will solve some example problems for the exam. Your exam. Do you want to talk about the exam first and then move on to the rest of the lecture, or?
Yeah.
Okay, so let's talk about the exam first. First, let's talk about your homework. Because I just, instead of posting it last week, I just posted the homework 3 today. So homework 3 will be due 16 before the class. Okay? But since you need the solutions for this homework for your exam, what I'm going to do is to make this homework, essentially, let's, I'm going to post the solutions. That's what I said. I will post the solutions tomorrow. So tomorrow afternoon, let's do tomorrow 12 p.m. or 5 p.m. Solutions will be posted Wednesday, which is March 10th, right? March 10th, 5 p.m., right? If you end up submitting the homework before this time, you will get an extra homework bonus points, right? So if your homework is worth 4 points, you will get, if you end up submitting the homework 3 before this time, you will get 4 extra bonus points, right? But if not, you can, of course, copy the solutions that I'm going to post and submit the homework next week and get the credit for it, okay? And yeah, last weekend for me was a very busy weekend. I didn't have the time to post the homework. So, which I guess is good for you, right? And yeah, that's for homework. So homework is posted today. It is due next week before the class, but I will post the solutions tomorrow. If you submit your answers before tomorrow 5 p.m., you will get bonus points, an extra homework bonus point, however you want to call it. Like, I'm not sure how many points are, how many percent of your final grade are the homeworks. I think around 4%. So you will get 4% bonus, okay? And it is definitely doable if you don't have any other homeworks, because you have to work on your exam anyways. So it is not a bad idea to work on this homework. We will do an exam review. We will solve at least one example problem for your exam, just to make sure you are clear on what to do. Your exam, I have designed half of the exam, so I already know half of the questions. But the other half, your opinion, your feedback, can be also included in the exam. The type of questions you want to see, if you let me know, I'll probably include it in the exam if I could. And when is this exam again? Okay, exam is, you don't read the syllabus, do you? Exam is on, we have an online question. Exam is on Thursday, March 11th, okay? And so let me write it on the board just to make sure. Exam 1, March 11. Chapters 1 through whatever chapter we cover, 6 of the Introduction to Flight book. And we actually covered a little bit of more advanced material. Those will be included in the exam as well. But we will mainly focus on the material of chapter 6 and chapter 3, which are the flight mechanics and the standard atmospheric conditions, okay? But you have to know the material from the other chapters, so also the material of chapter 6 anyways. So, yeah. Your exam, I have already designed half of the exam. Yes, I didn't, but thought we were off because of last week. So, someone is talking, is telling me about, so they were under the assumption that since we were off last week, we are going to postpone the exam, but I have already posted the lecture, right? Hopefully you have watched the lecture. We were not off last week, we were online. So if you haven't watched the lecture, make sure to go and watch it. And yeah. Yes.
So I have a materials exam at the same time.
At the exact same time?
The exact same time.
How is that possible?
You know how I'm in materials at the same time as this class? I take it asynchronously.
Ah, yeah, you told me about it. Okay.
Is this going to be like a 24-hour exam, or is it going to be like a in-class exam?
It is an in-class exam. What can we do? Is there anyone else who has a materials exam? Because we have a couple of other people who are taking the class online. No. Oh, materials. What I can do for you is to give you the exam just after your materials exam. But I assume you will be exhausted from the first exam. You don't want to.
Those vibrations, is that long? Or do we have enough time for that? I might be able to.
I think vibrations is next Tuesday.
No vibrations like this class. Can I take another hour in that class? Yeah, that'll work. That's fine.
I'm sorry. So after the class then, okay? So I'll probably just seat you in the conference room or in the main office and ask, do you guys know Coleman?
Where?
In the main office, the guy Coleman. I don't know his last name. No worries. I will ask him to proctor for you, right? And okay, you can also take it online if you want to, because I will post the exam online for the students who have taken the class online, and you are one of those. So you can take the class. I can open it to you on Blackboard. You can go anywhere you want to go.
You open it at like a random time. You're not on the Blackboard. I'm not on the Blackboard either.
Yeah, that's another problem. It is not fixed yet, huh? Just let's do it in person. I mean, I would rather, let me put it this way. I would rather everyone come in class and take the exam, right? Because you can only bring an equation sheet to the exam, right? And if you do the exam online, then it is very unfair to people who come in class, because I have no way of controlling people who are taking the class online. So how long will have to take them? Just a regular. So Vit is asking us how long will the let's just start with the examples. If you don't have any like random questions like one Nicholas had that is specific to you, let's start.
So most people are online. They're gonna get the exam online.
Yes, but if they can, yes, come.
And we're in class. We have to take the class. We have to take the exam in class.
That's correct.
That is already unfair as it is.
Why is that?
You just said the people online they could just.
Oh, because of the thing I said. Okay. Yeah, that's so. What I'm thinking. That's what I want to ask actually everyone who. I think we have everyone online as well. Is the exam in class for online students? So, yeah, the exam is online. So, if you we have everyone present in the online class. We have Emery, Vit, and Stephen. Can you guys come in the class and take the exam on Tuesday? Is it something you can do? So no, Vit can do it. And what about Emery? I haven't received a response from Emery yet, but hopefully we will come back. I can come. Okay, so it is only Stephen who cannot come in. What I'm going to ask Stephen do is to turn on his webcam, sit in front of his computer, turn on his webcam to imitate the exam environment. Okay, so he won't be able to cheat. I mean, I trust you. There's no problem with trust. I definitely trust you, but I just have to make it fair to everyone, right? That's the best solution I can come up with. Okay, because I don't want to make the exam open book, because it is an easy exam by itself. If I make it open book, then it won't assess you on your knowledge of the class. Does it make sense? Okay. Yes. Okay. So if there is no any other questions about let's call them random stuff that comes to your mind, let's talk about the exam policy and number of questions you're going to get on the exam. Okay. So exam policy. Exam will be 75 minutes. Okay. We are going to start at 10:05, 5 minutes past 10, and we are going to end at 11:20. As I said, most of the question will be focused on Chapter 6. We are going to use some material from Chapter 3 as well. But in general, you have to understand the lift coefficient. You have to have basic understanding of aerodynamics to be able to answer Chapter 6 material as well. So I won't ask you to calculate lift specifically. That's what I mean when I say I won't give you any questions from Chapter 5 or Chapter 4, right? But you have to have an understanding. Okay, you will be able to bring an equation sheet, two-sided equation sheet, okay, to the exam. And but most of the exam will focus. So let me put it this way: I will give you a specific flight condition, and I will ask you to find the equations of motions, right? For most of the problems. So an equation, if you don't know how to do this, an equation sheet won't be helpful, right? So you have to understand how to write a force balance. You have to understand how to find an equation sheet. But we will mostly focus on the two-dimensional flight that we have focused on for most of the flight mechanics part of the class. So you don't need to go through all of those huge equations we had, right, during the exam. But make sure to have them in your equation sheet, just in case, right? And yeah, that's for the equation sheet. I'm thinking of, let me close the door. This. I'm thinking of giving you 4 questions, right? 4 problems that you need to solve in the 75 minutes. And but I have already designed only 2 of them so far. So we have 2 options going forward. I can design the 2 other questions for you, right? Or we can replace one of the problems with descriptive problems, a couple of them, not just, in which I'm going to ask you, explain to me what is a level flight, right? Just one-liners or two-liners, right? Nothing very fancy, nothing very, or how can you get the minimum power? What should be the relationship between lift and drag, lift coefficient and drag, or what should be minimum, right? We have talked about this. You have the equations. You should know the concepts. So 2 options. It all depends on what you want to get during your exam. Which one do you prefer? Let's see. That would be great. Second one. Huh?
What's on it so far?
2 problems.
2 analytical problems?
2 problems that, yes, you have to solve. You have to find an answer for. Yeah. So let's take a vote. We have 2 online votes for the, I guess, for the second part.
So it'll
Sec-
only be 2 questions if we take the second one?
It will be 3 questions and 5 descriptive problems. But those or multiple choices. But those descriptive problems will be, the answer to those will be like 1 line or 2 lines, right? You don't have to like keep writing. If you don't know the answer, I assume you won't be able to find it in your equation sheet, right? So that's the trade-off. It will be easy questions, but if you don't know the answer, you either have to cheat or you just have to lose a point. Okay. So we have 1 vote here for the problems, 2 problems, 1 vote for descriptive problems plus 1 problem. Let's vote here. Just the normal 4 problems. Okay. Normal 4 problems. 4 problems.
I'm going to abstain. I don't feel confident enough in either choice.
Okay, so we have, I guess we have 4 votes for the regular problems. Okay, so I'm gonna just give you only for 4 problems. But all of these problems are going to have different sections. So I'm going to ask you to calculate this, then calculate this, then calculate this, then calculate. You can think of those sections as hints, right? So instead of telling you that these are the situations, give me this, I'm going to make it a step by step. So you're getting some hint. This is the first thing you need to calculate. Then this is the thing. Then this is the thing you need to calculate. And what else? I won't ask you to, I will give you whatever you need. So you won't need to look up a table. So you don't need to bring in any tables, any aerodynamic tables or anything with you in class. And if I've missed something during the exam, just let me know as soon as you read the question. I will write it on the board, okay? And I will, that's homework. Just make sure you are clear on the homework 3, which was posted today. And I guess that's it. Is there any other questions about the exam? Okay. Okay, so let's finish chapter 6 or flight mechanics. One of the last things we want to talk about is the turning flight. And for the turning flight, we are going to talk about 3 different conditions. One is a level flight with a bank angle, which means that you are going to turn around the circle, right? One is a sudden increase in lift during a level flight, and then a sudden decrease in lift. Okay, so let's talk about the first situation here. This is, let's say this is your front view of the aircraft. This is the horizontal line, and this is the vertical line, the horizon line. Your lift is going to be normal to your flight path. Your weight is going to be in this direction. But we also are going to have a centrifugal force, right? Because we are turning around the circle. If you want to have a top view of this, this will be your top view. You are turning around the circle. Of course, you usually don't close off the circle. You're just going to turn and then do the bank angle. Okay, so, and the bank angle here is going to be this angle, phi. Okay, what would be the equation of motion for this flight in this direction? Equation of motion would be L cosine of phi equals to W. And here phi is the bank angle. Just have to be careful about these angles because we have used all of these Greek letters for different angles. Just have to make sure that you are clear on which one refers to which angle for which situation. Okay. So bank angle and turn angle. We have the equation of motion. That's the equation of motion in the y direction. Okay. How can we calculate your centrifugal force? What will be the relationship between the lift and weight and the centrifugal force?
It'd be L sine theta plus centrifugal, or sorry. Yeah, L sine theta plus centrifugal force minus, I guess W from B in the X.
Okay, but we need to include W there as well, right? So what I'm going to do here is I'm going to move lift down here. What does this look like? A triangle with a 90 degrees angle here. So you can safely say your centrifugal force is equals to L squared minus Y squared for this specific condition, right? For a level flight with a bang angle or level turn. That's actually, this is a level turn. Level turn with a known bank angle. Okay. And we are going to introduce a new term called the load factor. And we can rewrite this centrifugal force as a function of this load factor. Is going to be equals to n squared minus 1, right? Of course, I forgot the W here. W n squared, square root of n squared minus 1. Okay, so is there any way for us to relate this centrifugal force to velocity? How? This is a centrifugal force. Force equals to m times acceleration.
Whenever lift equals 1/2 rho infinity squared.
No, just use this equation. F(r) is equals to ma, your Newton's second law. What is the centrifugal acceleration? Centrifugal acceleration. Centrifugal acceleration. We have a linear velocity. Pardon me? That's it. mv infinity squared over r. So an m here is w divided by g. So let's replace that here. We are going to get w divided by g, v infinity squared over r equals to square root of w square root of n squared minus 1. Can cancel the w's, and r here is capital R. And rearrange everything to give us r. Okay? So your r is going to be v infinity squared divided by g square root of n squared minus 1. This will be your, this is called your turn radius. Another parameter that is important here is how fast you are turning, right? What is your radius? That's an important parameter when you're turning. Another parameter is how fast you are turning. What is the value? What is the parameter? What is the variable we can calculate to characterize how fast we are turning?
Rolling.
Your
To see
how fast you're turning, right? How fast? Angular velocity, or we are going to call it turn rate here. So d theta divided by t, right? Angular velocity. So your angular velocity is going to be equal to g square root of n squared divided by v infinity. No.
it's missing another v infinite.
How did we, okay. How can we get from this turn radius to omega? That's it. So it is not just the inverse of radius. You are going to divide it by a v as well. Okay? We have v infinity squared, right? So turn rate and radius. That's for your level turn. Let's consider another situation that you are in an unaccelerated flight, and then you will see a sudden increase in lift. What is going to happen to your airplane? It should.
Level flight.
We are in a level flight. You will see a sudden increase in lift.
Pitch up.
It will pitch up. So you are going to start pitching up, right? What is the equation of motion for this case? You have lift, you have drag, and you have centrifugal force. Okay? Your centrifugal force, lift equal to drag, your centrifugal force has to be equal to
Your weight.
lift minus drag, right? Lift is going to be higher than that. So based on this, we can actually find the centrifugal force as W multiplied by n minus 1. Your turn rate can be equal to V infinity squared divided by n minus 1 instead of the square root, turn radius. And turn rate, omega, is going to be divided by V infinity. Okay. What about the third condition? what is going to happen to, this is actually called a pull down, the third one. Pull up and pull down. Okay? How can we find how can we find the rate and omega during a pull down? So this is how we are flying in a pull down, right? It is not just losing altitude, you are actually pulling the aircraft down. So you are in the reverse position, right?
Why is lift pointing down?
Because you are going to change the orientation of the airplane to be able to go down, right? You are not losing lift. That's the point here, right?
So you're upside down.
You're upside down. That's what I'm saying. I forgot the word upside down. Not my native language, guys. This happens. So your centrifugal force is going to be equal to L plus weight, which is going to be equal to W n plus 1. And your R is going to be the infinity squared, n plus 1. Your omega is going to be G n plus 1 divided by V infinity. Okay? Okay, Steven is asking us for the FR. That he said the drag, which confused me. Okay, so here, this W is weight. Here, this is omega. How can I differentiate these two? I'm going to use W, weight. Okay. So, what will happen to our equations if your load factor is much larger than 1?
Your angular velocity goes up.
What will happen to the equation, not the angular velocity and the turn rate and turn radius? You can.
Generate more lift.
What changes can you see? How can you simplify the equation if your n is much larger than 1? You can
get rid of the square root.
You can get rid of 1, right? So if you get rid of 1, you're essentially getting rid of the square root, and you can get rid of 1 in those equations. You are going to get unified equation. For this case, your omega is going to be Gn divided by V infinity. Your R is going to be V infinity squared divided by Gn, right? Okay, so as you can see, when you are in a turning flight, your turn radius is, of course, important. Your turn rate is important, and they are both functions of your load factor. But what is the goal here? What do we want to do? Do we want to have higher turn rate or lower turn rate? Do you want to have higher turn radius or lower? Okay.
If it's something where it's like military or performance based, you want a really high turn rate. But if it's a passenger aircraft, you probably wouldn't want to be yanking people around.
Exactly. So essentially, if you are considered with maneuverability, you are going to need a very high turn rate and very low turn radius, right? But if you are more concerned with stability, which is always the argument we have, which way we want to go, higher maneuverability or higher stability, right? If you want to have higher stability, you're going to need higher radius and lower turn rates. Is there any question so far? Okay. Is there any way for us to relate these equations to lift coefficient specifically? No. We had one no. Did I hear no?
I said yes.
You said yes. So how can we relate turn rate and omega to lift coefficient?
The load factor.
Load factor is an important parameter, so we don't want to remove the load factor from the equations, right? And that it is a design parameter. You want to always keep a design parameter in there.
Omega is BR. Omega is BR.
Okay, so how would you relate that to CL?
1/2 rho v squared is CL.
Okay, so CL, you are moving in the right direction. So we define CL as 1/2 rho v squared. What else? We define lift as 1/2 rho v squared CL, right? CLS, right?
We can rearrange for V infinite there.
Exactly. We can rearrange for V infinity. And 2L rho S, right? This is what you're going to get as CL. Okay. So we can actually plug the V infinity there. In the turn rate equation, let me clean this part of the board and plug it in there. So your rate is going to be equal to square root of 2L. And V infinity is to the power 2, so we're going to get 2L rho SCL divided by your load factor, which is G for that specific level term, right? And your omega is going to be equal to G square root of whatever divided by the square root of 2L rho SCL. But here we are in a level flight. What does it mean? We are in a level flight. Let's say we are in a level flight with a very small bank angle. What would this mean for these two equations? We can replace lift with weight, right? So what will happen to you if you do that? Your R is going to be equal to 2 W divided by S divided by rho CL divided by G. So two design parameters have appeared. Wing loading, load factor, and wing loading. Also the CL, lift coefficient, in your R. You can do the same for omega and get the equation for omega. Of course, we can replace V infinity in these equations, yes.
If your lift equals your weight, doesn't that n equal 1 heading by 0 essentially?
That's a good question. So we are going to talk about it then in like 5 minutes. But essentially, let's talk about it in 5 minutes. Is there any other questions? Let's actually address Igor's questions first and then move on here. What we do here, we are going to use V infinity, find V infinity as a function of lift for the level flight before you start turning, right? When you start turning, your load factor is not going to be 1 because lift is not going to be equal to weight anymore, right? Does that make sense? Okay. You're either going to lose some weight or going to gain some weight, lift, right? But that's a good observation. So let's see what else do we have here. I guess that's it. How can we maximize your omega and minimize your radius? To maximize your omega, you're essentially going to have to maximize your n, right? To maximize your radius, you have to minimize your radius, you have to maximize your n again. Let me actually give you these final equations after that relates. I mean, we have already done this. These are the general equations for case n is much larger than omega. Let me write them down. You can simplify the other equations to get this, to get to this. And your omega is going to be equal to g square root of rho infinity CLN divided by 2. Okay. So let's talk about the Venn diagrams. Venn diagrams are some things that you are going to see a lot in for an aircraft. If you are going to design an aircraft, this is something you will definitely get. Use another. So on one axis, we have the load factor. On one axis, we have V infinity. Okay. And this is usually how it looks like. Let's say you are at this point, point A. What does this tell us? That you are going to get for a specific load factor, for a specific velocity, you are going to get this maximum load factor. Okay? And keep in mind that N is defined as L divided by W. So to get the maximum turn rate and minimum radius, this is how much you can go. Right? What does this mean? There is a limit to your factor, to your load factor. But why do we have this limit? You can only increase the lift so much, right? By increasing your angle of attack. So what is going to happen after this line?
Probably damage to the aircraft or the
Before the damage happens, we are increasing the lift by increasing the angle of attack, right? So these lines represent your stall condition. Okay, on both sides. So if you are flying with this velocity, at this load factor, this is not your maximum load factor, so you're not going to get the maximum turn rate and minimum radius. All right, does that make sense? But there is a point after which, if you increase the velocity, you can increase the velocity so much, otherwise you're going to get a structural damage. As Trey pointed out, there's also these limits for load factor. So theoretically, at this point, you can increase your lift more to get the N maximum, right? But you will get into the structural damage region.
So the stall starts occurring after A? Or is that?
And in this region. Let me use, so this is your stall region with the orange. Okay, so there is this interesting point, right, for a specific velocity, which you will get your maximum N, right? And that's the maximum N not for a specific velocity, that's the maximum N for aircraft, right? If you increase the N afterwards, with keeping the velocity constant, you get to the stall condition. If you increase the N afterwards with increasing the velocity, you're going to get to a structural damage, right? And we can, if you have the maximum N for the aircraft, we can simply find the velocity. Sorry. We can simply find the velocity at that location. This is called V star. 2N max. Of course, we are going to have maximum CL as well, because afterwards we are going to get the stall condition and then also the wing loading. Okay? And this is called the maneuver point. This point, maneuver. I always forget this one. Maneuver point. The reason it's called the maneuver point is because this is the maximum N you're going to get, which means that you are already at the maximum turn rate and the minimum radius. This is the best maneuver you can get out of the airplane. Okay? Do we have any questions? So let's see what Steven is asking here. We're at increasing lift FR. What is that W? I'm not sure what you're referring to. This is weight, force balance. This is also weight. But here we have omega. Oh, it's gone now. Sorry. Okay. Any questions? No. Yes.
This is a pretty tangible point. Like the pilot can feel it, like the maneuver point, right? Something. I guess doesn't it might depend on the model.
What do you mean the pilot can feel it?
Like, I guess we talked about this a bit in systems, but like the feedback from the controls to the pilot, like is the maneuver point. I'm assuming there would be probably some disruptions in the flow over the wing, so it would probably be a little shaky. Would that be enough for the pilot to notice where he's about at the tipping point?
Okay, thank you. But that's a good question. Think about it this way. You are at a point at which if you increase the angle of attack a little bit, you will get to the stall condition. I'm not a pilot, but I'm 99% sure that you will definitely feel what is going on, right? Because the controlling the aircraft at that point is going to be very, very hard, very tough, right? Because you're at the tipping point, right, as you mentioned. But yeah, you will definitely feel that, yeah. Because you're at the point you're either going to get a structural damage, which means that you will feel any structural damage, right? If you're or you're going to lose a lot of lift, right?
So is that? I'm wondering why we call it maneuver point. Is that like where peak maneuverability happens?
That's what I said, yeah, exactly.
So you're the most maneuverable, but you're also like very close to stalling if you go a little bit slower.
Why is that? Why do you think that's where you get the most maneuverability? Okay, you're essentially getting your highest lift coefficient, right? That's the point where after which you're going to get the stall condition. But something to keep in mind is that we are always trying to stay very safe, right? So we usually don't get to these points in your design, right? I assume you are definitely going to have this discussion in your aircraft design course if you are going to take an aircraft design course. Okay, so let's move on and let's talk about the energy levels, which is the last part of the class. We are going to talk about accelerated flight a little bit. And this is something that you need to understand, right? Because understanding it is not that you already know a good deal of this, okay? And you already know a good deal about energy balance, like force balance, all of those things, right? So writing an energy balance for an accelerated flight is not that hard to deal with, okay? So we can define the specific energy of an aircraft as its energy divided by its weight. We're going to call this H of E. It stands for the head, which is your potential energy plus the kinetic energy divided by your weight. Okay? How can we calculate the potential energy of something? mgh. Exactly. And how can we calculate the kinetic energy of something? 1/2 mv infinity squared divided by your weight. Okay? So your specific energy of the aircraft is defined as the altitude plus v infinity squared divided by 2g. Okay. Based on this idea, we are going to have energy lines for Mach numbers, energy lines for each, I guess, flight conditions, you can say. So H of E versus your Mach number. The idea here is that your energy lines are going to look like this. These are the lines. Energy lines are lines on which H of E is constant. Okay. So what does this mean? It means that this is altitude, and your energy here is an energy head. Keep that in mind. Altitude. So you're always dealing with feet or meters or whatever, kilometers. On this energy line and this point of this energy line, you have higher potential energy, right? On this point of this energy line, you have lower potential energy and higher kinetic energy, right? So essentially, based on what we have here, how can a pilot increase the kinetic energy, meaning increasing the velocity, right, without adding any energy to the system? Decreasing altitude, right? That's the idea. You will have always the potential energy, and you can convert potential energy to the kinetic energy, and vice versa. So moving on these lines is easy for the pilot, right? But it's going to be harder to get from one energy level to another one. Okay? Let's talk about it. Let's talk about an accelerated flight. For an accelerated or accelerated climb, with a flight path angle theta. Okay, and thrust vector 0. Okay, so what is the equation of motion for this specific type of flight? We have two equations of motions. Of course, that's all we have done. In the x direction, in the horizontal direction, you have T thrust minus your drag minus your weight sine of theta, right? For an unaccelerated flight, we said this is equals to 0, but for an accelerated flight, this is equals to m dv dt. What about the other direction? Oh, let's just work with this direction because this is what we need. Okay, let's move on to let's move w sine of theta to the other side. T minus d is equals to w sine of theta plus dv dt. And let's multiply all of these with a v infinity. So tv infinity minus dv infinity equals to wv infinity sine of theta plus m dv dt. Okay. Let's move w to the other side. tv infinity minus dv infinity divided by w is equals to v infinity sine of theta plus 1 over g dv dt. Oh, there's a v infinity here as well. V infinity. That's v dv dt. What does this part remind you of? How does it remind you of vibrations? Just because of the sign?
Yeah, the amplitude in front of the sign and W for omega. Sad.
Well, vibration is a good course, isn't it? Okay, you don't like it then.
Difficult.
It is difficult. And this is weight. Just since Lawson was reminded.
At the end of the second equation, where's that v infinity go? Is that
That's
after
m, it doesn't, m multiplied by v infinity multiplied by dv dt. But what does this part remind you of? This was the unaccelerated climb, right? We did an analysis for the unaccelerated climb, and v infinity sine of theta is your vertical velocity, which we call rate of climb. Okay? Okay. What did we call this one, this part? Does anybody remember? No one? We called it excess power, right? This was thrust available, right? A power available, and this was power required, right? That was the idea. If your power available is higher than power required, you are going to climb, right? So the only part that acceleration adds to it is v infinity dv dt. Okay. If you look at this more closely, v infinity sine of theta is your vertical velocity. How do we define the velocity? Is the changes in altitude, vertical velocity, changes in altitude with time. So this part is actually, I'm writing this part here first, dh divided by dt. Okay. We can, of course, take the v infinity inside this derivative, right? Or we can just take the derivative of the kinetic energy, right? That's, you have v squared divided by g, right? Divided by 2g, right? Take the derivative, is going to be v divided by g dv dt, right? With respect to time. So this is going to be your derivative of kinetic energy. I'm going to just write it as is. dv dt is equals to the power itself is the changes of the energy height with respect to t. Is there any questions? No. Okay. So for an accelerated flight, this is what you are going to get. Or we could have directly used the energy method instead of the equation of motion, right? We could have just took the derivative of the energy balance there, and that would have given us the changes in energy of the system, changes in the altitude of the system for a specific acceleration. Is there any questions? There are a couple of things that remain here, but those are mostly conceptual things. And I'm going to just skip them. We'll talk about them in the next lecture, but it will take like 5 minutes. But we only have 10 minutes of the class remaining, and I want to make sure that we at least talk about an example problem. And this problem was an exam problem for previous year. But this is not this is the type of problem you are going to get, but with not this many sections, right? Because you're going to need a lot of time to work on this. So let's try to solve this together. We have an aircraft carrier. Okay, we have an aircraft carrier. Carrier. How do you pronounce this one? That uses a catapult system to catapult the planes. Okay, to launch aircraft. From the limited distance available on the dock, we have a limited. During the launch, maximum thrust is also applied by the aircraft. Okay, in general, the ship will have a forward speed into the direction of the wind. Okay, and we want to improve the takeoff performance. The following data are available. We are given some data for the wind speed, ship speed, all of those things, but we are not going to use them. I'm just going to find the equations for you. And the first thing that we are asked is to draw a clear free body diagram in which all the relevant forces are indicated. So this is something you definitely need to do for most of the problems on the exam, right? So free body diagram. Okay. On an airplane that is on the dock. So let's say this is a plane, a very interesting plane on the dock. But what are the forces that we have here?
Gravity.
We have the weight force, right? That's what you meant, right? Okay, what else? Thrust. Okay, that's the engine of the aircraft's thrust.
Thrust from the aircraft carrier.
Thrust from the catapult system, right? Let's call it T of C. What else?
Drag.
Drag. What else? Lift. That's it? Or is there any other thing?
Do you know any, that's in depth, like if the aircraft carrier is turning or anything?
It is not turning.
Would you have a drag? Well, I guess you could consolidate it, but I guess you could consolidate thrust. Would you have a drag due to the catapult?
No. Well, no. Think of catapult as like a rolling, a escalator, whatever you call it. It is called an escalator, right?
Oh,
You have seen like
a newer catapult on an aircraft carrier then. Okay. I don't know why, but I thought of like an old one.
yeah, no, you are not.
Just like.
It is definitely not a literal catapult.
They just like.
Yeah, no. But okay, so what is is there any other forces? Let's see if there is any online. Okay, we have one correct answer here, and that is the friction force.
Is it catapult? Is there gonna be some centrifugal force too?
No. Because it's essentially something is moving on the ground and taking the aircraft with it, right? So your ground is moving, right? Think about this, right? But we are going to have the friction force in this direction as well. Let's call it F of R. Okay. So we have a free body diagram, and that's it. The next part is asking us to derive the equations of motion for the aircraft during the acceleration over the ship deck. We can assume that this catapult is uniformly accelerated. The mean acceleration must be calculated at the characteristic speed v end. But so we can use an average acceleration, which can be calculated using the end velocity. End velocity is the velocity you're going to get at the end of the deck, okay, divided by a square root of 2. Okay? Pardon me?
Why is it over root 2?
That's taking the average. If you take the mathematical average, it is not equal to that, right? This is the average velocity you can use to calculate the acceleration. But this is given to you. You don't need to do any calculations for it. So let's do this. Let's find the equation of motion for this case. Equation of motion. On a free body diagram, you just have to make sure that you define your axis as well. In the x direction, what are the forces that are present here?
Two thrusts, friction, drag.
2 thrusts, exactly, plus friction, plus minus friction, is equals to
Zero. The average acceleration.
m dv dt, right? Your acceleration. Okay. What about the y direction? L minus W is equals to 0. Exactly. So your lift is going to be equal to weight. Is that it? Okay, let's go one by one from Igor. Tell me if you see anything that is missing here.
When there is friction, can there be a normal force that generates the friction?
Exactly. So we are missing the normal force, right? Okay. So your normal force is going to be equal to L minus, this is equals to 0, and minus W. Okay, so we have the two main.
What? Wouldn't it be equal to W minus L?
That was my mistake.
Is normal force
I'm sorry. Last time was correct, W minus L. I don't know why I changed that there. Okay, so, yeah. So we have the two equations of motion. We have the two main equations of motion. And how can we find this friction force? Mu multiplied by
Cosine mg and mu mg cosine mu.
so mu the only thing that happens here, the only force you're going to have is mu multiplied by the normal force, right? Which is going to be mu multiplied by W minus L. So you have your equations of motion, and that's the answer to part B. Let me get the part C. Part C is asking us to derive an expression for the ground run distance S of deck, right? In terms of a mean acceleration and the speed at the moment the aircraft leaves the deck, so V of end. And yeah.
So the takeoff distance and the final velocity.
The thing is, it is not exactly the takeoff distance because you have to make that distance the takeoff distance. You don't have any other distance, right? You are limited to that distance, right? That's why we have the catapult. Okay. How can we find that distance? This S of deck is equal to the integral of V dt, right? From 0 to V end. Is this correct? How can we take this integral? How can we change this equation in a way that is going to help us take this integral? So the easiest way to take this integral, because we don't have any other information, right, is to somehow change this dt to a dv, right? How can we do that? go back to the definitions of acceleration for a solid body, dv dt, right? So let's plug that in. Integral of 0 to v end, v divided by a dv. The idea was we can use an average acceleration, a bar. So we can take it out of the integral, v to v end, v dv. Okay? So what is the solution to this integral, v dv? What is the solution to that integral? v squared over 2, right? We have 0 for one of the limits, v end for the other one. So we're going to get v end, whatever that velocity is, divided by 2 your average velocity. That will give you s of deck, average acceleration, v squared. Okay. So and the next part is actually asking, that's part D, right? Part D is asking us to find that's part E, to find the acceleration for this specific case as a function of v end. Okay, we are already told that it is related to v end by v end divided by a square root. That's essentially the acceleration at that location, where the velocity is v end divided by a square root of 2, right? But we are asked to find that acceleration. And how can we do that?
You have the end.
The what?
You have the end.
V end.
Yeah.
No. We don't have v end. Let me actually check. No. So it is a parametric. We want to find a as a function of v end. Right? So we want to find an equation. A equals to v end squared plus 2 v end plus 3 plus 5 plus whatever. I didn't hear you.
You have the mass of the aircraft?
You have every other thing except for v end. So essentially, the final equation you are going to find is exactly the same as I said, like 2 v end plus 3 v end squared plus whatever. But so let's just forget about what you have and what you don't have, right? I have asked you to find an equation for acceleration that includes v end. Which one? No. Are you talking about that top thing? That I'm saying that over there, I've said that average acceleration is the acceleration you are going to get when the velocity is equals to v end divided by a square root of 2. So that's the point you are going to use the acceleration from as the average acceleration. Okay.
What would you just do v final minus v initial over the distance? Find like the slope, get acceleration.
But that just, you're just assuming that you have constant acceleration, right? Yeah. No, that's which integral? Which one is that one? Are you talking about this one? This is not an equation. This is nothing. A average. So let's say this is 0. This is s of deck, right? At each location, you have a velocity. Velocity 0, velocity v end. At some location here, your velocity is equals to v end divided by a square root of 2. This is a point you are going to take the average acceleration from. So the acceleration at this point is your average acceleration, okay, in our calculation. Okay, so let's do this. How can we find any equation for, based on what is written on the board, how can we find any equation for acceleration. Just forget about V end, any equation for acceleration.
F over M.
F over m, okay?
You take the X equation and divide it by the mass of the SF.
Okay, that's the first, exactly, that's the first step, right? So we already have an equation for acceleration, right? And in this equation, thrust, catapult thrust, all of those things are given to us, right? And those are not necessarily a function of V end. But what is the function of V end? What is a direct function of, in your forces, which one is a direct function of your velocity? Let's say thrust is constant. Okay, I think I said that, right? And how would you relate thrust to velocity? What time is it? 11:25. Okay, we are already over time, right? So we have drag Q1 rho V infinity squared SCD, right? We also have lift 1/2 rho V infinity squared CDL. So this is where your velocity appears, right? This is where you have the velocity, right? Then you have then you put in the lift coefficient, drag coefficient. I wish we could have solved this problem completely, but we don't have the time. So
You said this is before these problems of the exam?
yes. I mean, the problems. This is not a very time-consuming problem, right? The free body diagram, right? Let me just disconnect everything, and then we can actually talk more if you want after the class, but we have to leave the classroom. So let me just disconnect everything.